Welcome and thank you for watching our presentation on network dynamics and node behavior analysis within our dataset, Facebook. Our study leveraged a dataset from the Stanford Network Analysis Project, focusing on Facebook's vast landscape of friendship connections. This research aims to unravel the complexities of how users interact within this network, employing various network analysis metrics and the methodologies to shed light on the patterns of connectivity and node behavior. Our findings offer insights into the broader implications of social networks on information dissemination and community formation. Our presentation contains 4 parts. The first one is the introduction, the second one is the network property, and the third one is node behavior analysis, and the last one is conclusion. Our investigation centers on Facebook's dataset, which maps out the friendship connections between Facebook users. Each node represents an individual user, while edges signify the friendships, forming an undirected network. This dataset is invaluable for exploring ego networks, where each network is centered around a single node, providing a microcosm of the larger social fabric. By combining several ego networks, we obtain a comprehensive view of social interactions on Facebook. The dataset's de-identified nature ensures privacy while allowing us to analyze patterns of connectivity and social behavior within this digital ecosystem. In analyzing the network, we focus on several key metrics that offer insights into its structure and dynamics. On the left-hand side is our node visualization, and on the right-hand side is the degree centrality, which is a measure of the number of connections a node has in a network. There is a long tail on the right side suggests a few nodes have significantly higher connections than the rest, which is a characteristic of scale-free networks. Most of the degree centrality falls between 0 to 0.05, indicating that most nodes have few connections and a small number of nodes have many connections. For the betweenness centrality, the histogram indicates the distribution of betweenness centrality values across nodes in the network, which is heavily skewed towards the lower end, indicating a network where many nodes are peripheral and a few nodes are highly central. Given the skew, there are likely only a small number of nodes with high betweenness centrality. These nodes could play a crucial role in facilitating the flow of information or resources across the network, as they lie on many of the shortest paths between other nodes. Also, networks with a few highly central nodes often exhibit scale-free properties. In such networks, the majority of nodes are not well connected, but there are some hub nodes with an exceptionally high number of connections that dominate the network structure. For closeness centrality, this metric measures how close a node is to all other nodes in the network, reflecting its ability to quickly interact or spread information across the network. As shown in the graph, most nodes have a closeness centrality around 0.3, indicating that on average, nodes are not too far away from each other in terms of path lengths. But there's room for improvement in network connectivity. Also, the spread of values indicates variability in how easily different nodes can reach the rest of the network. Some nodes are relatively isolated, those with lower centrality, while others are more central. Nodes with higher closeness centrality values are generally more efficient in spreading information through the network, as they can reach other nodes in fewer steps on average. The presence of nodes with high closeness centrality suggests some nodes are well positioned to quickly interact with most other nodes. As for eigenvector centrality, the histogram shows that most nodes have a very low eigenvector centrality score, since it measures the node's influence based on the principle that connections to high-scoring nodes contribute more to the score of the node than equal connections to low-scoring nodes. The distribution suggests that there are very few highly influential nodes in this network. The presence of a few bars at the higher end of the scale would indicate the existence of a small number of highly influential nodes.
Now we are going to talk about network structure metrics. The first one is clustering coefficient. The graph shows there's a wide range in the clustering coefficient values among the nodes, indicating diversity in how nodes are embedded in their local neighborhoods. The taller bars at higher clustering coefficient values near 0.6 and 1 suggest that many nodes are part of tightly knit communities, where their neighbors are also connected to each other. Nodes with moderate clustering coefficients around 0.4 to 0.6 might indicate regions in the network that are somewhat connected but not as densely knit as those with higher values. The existence of bars at the lower end of the clustering coefficient scale, near zero, indicates there are nodes with few interconnections between their neighbors, which could be more isolated or peripheral nodes within the network. The second one is average path length. The most common shortest path lengths are between 2 and 4 steps. The average path length is 3.69. This indicates a small world characteristic of the network, where most nodes can be reached from any other through a small number of steps, despite the network size. Path lengths of 5 to 7 steps occur less frequently, suggesting that while most of the network is closely connected, there are certain parts of the network that are more isolated or serve as bridges between dense clusters, and the longest shortest path appears to be 8 steps, which indicates the maximum distance between the most distant nodes in the network. To further our understanding of the network structure, we use the Loving method to detect communities. The first graph directly visualizes the original network G using the spring layout, which considers all edges and nodes for layout purposes. The second graph intends to identify the most influential nodes within each community based on degree centrality. For example, the most influential node for community 0 is 0, and the most influential node for community 1 is 348. Overall, this network shows a complex pattern of connectivity with several dense clusters, probably communities, and many interconnections between these clusters. The dense areas with a single color likely represent communities where nodes are more connected to each other than to nodes in other parts of the network. There are also nodes that appear to serve as bridges connecting these communities, indicated by the lines stretching between the clusters. After generating a random graph with the same number of nodes and the probability, we compared the average degree, clustering coefficient, and average path length between them. Both networks have nearly the same average degree, which suggests that the average number of connections per node is similar. This is an interesting observation because it suggests that despite potentially very different topologies, on average, each node in both networks has about the same number of connections. There is a significant difference in the clustering coefficient, with the original network have a much higher value. This indicates that the nodes in the original network tend to cluster together much more than in the random network. In other words, there's a higher tendency for the original network's nodes to form tightly knit groups with many interconnections.
Okay, the next part is node behavior analysis. So I'm first going to talk about node connections and interactions. So we visualize the significant nodes according to their degree. The top 10 are painted red in the graph on the left. The graph shows that these nodes tend to gather in the same areas, representing the users with the most connections tend to stay in the same communities. So the graph on the right is the close-knit centrality graph. So the darker the color is, the lower the close-knit centrality is, and the bright green area is those central nodes having the most close-knit centrality. So they are central and can spread information efficiently within their reach. And there are also those purple nodes, which are users with fewer direct connections. And the next part is node contributions. So we have those two graphs, eigenvector centrality distribution and clustering coefficient distribution. The first one, the graph on the left, eigenvector centrality distribution, implies that there are nodes which not only have many connections, but are also connected to other well-connected nodes. This might indicate the presence of leaders in the network who contribute significantly to the network's connectivity. So the clustering coefficient distribution, the graph on the right, shows the variability in the network's tendency to form cliques. A high clustering coefficient for a node means its neighbors are also likely to connect to each other, which could contribute to a strong community structures. So the last part is the impact of node behavior on network dynamics. So we visualize the graph when deleting the significant nodes, so the top 10 degree nodes I mentioned earlier. It is very obvious that the graph seems very less connected after deleting those nodes. So the users who act as leaders in the groups and communities are crucial for the connection within the social network, and their disappearance may lead to a great disconnection within the social network. Removing those pivotal users may lead to, firstly, the reduced connectivity. So visualizing the removal implies a substantial reduction in friendship links, potentially leading to a sparser network, increased average path lengths, and slower information spread. The second outcome is the altered community structures. So their hypothetical removal suggests that some communities might lose cohesion, leading to restructured social groups or isolated clusters. And third outcome is limited content spread. Without these nodes, content propagation could face severe restrictions, decreasing the reach and engagement levels of the content across different communities. So the last is shifts in user behavior. The absence of significant nodes might prompt users to seek new connections and content sources, potentially altering their engagement patterns on the platform. While some may explore new groups and contents more actively, others might disengage due to feeling disconnected from the mainstream social medias. So in conclusion, our comprehensive analysis on Facebook networks through various metrics and comparative studies illuminates the patterns of connectivity and the pivotal role of node behavior. By analyzing the network structure and dynamics, we gain insights to the mechanisms driving social interactions and community formation. This research not only contributes to our academic understanding of social networks, but also offers practical implications for designing more effective communication strategies and enhancing social media platforms. Thank you very much.